So today we're going to talk about optimizing the networks in two senses. First, about the optimizers themselves, the algorithms that will use the information on the gradients to change the weight of the network, the parameters we're trying to adjust. Optimizing the way the network is training, so how we initialize the weights, how we adjust the learning rate and so on, and also optimizing the performance of the network by mitigating these problems of overfitting, eventually underfitting if the network is not adequate, and using regularization. But first, I just want to give you some heads up about this. The tasks are already marked in Click. These are the dates. The first assignment, we will have to submit it until May 8th, so there's still some time. But you should form the groups. The assignments should be in groups of 2 students, and you should form the groups until April 24th. Because from April 25 to May 8 would be the period for submitting the assignment. This would be a bit extended, but this way you can choose to submit the assignment before the test or after the test, and we avoid falling exactly on the same date of the test. Okay, so you have some margin there to decide when to submit it. I'm going to present the assignment next week. There is still some subject matter we need to cover, but from then on you have time to think about it and to start working on it. On the week of 28 and 29, these tutorial classes will be reserved for questions about the assignment if you need help with anything. Okay, so for now, the important thing is to check the course site. You have instructions there. Basically, you need to send an email here indicating your group partner. This is the same thing as you did last semester in machine learning, but you have the instructions there, and this should be done until 24th of April. Okay, so now let's start with the optimizers. The optimizers are those algorithms that we use to adjust the parameters of our network based on the information on the gradient. So far, you've been using the stochastic gradient descent, the SGD, that allows you to use momentum or not. And you saw in the code that what you do is you use gradient tape to get the gradient information, and then you use the optimizer to apply that information to change the actual parameters. And this is done taking into account the learning rate, things like momentum, and other more sophisticated approaches. So basically, we want to minimize the loss function. We saw last week, in general, this is basically the cross entropy between the probability distribution each specific instance of our model will give us about the data, and the actual distribution of the data as we get it. But this is basically the maximum likelihood solution. The details on how to do this, the numerical optimization part, are outside the scope of this course, but it's important to understand at least at a higher level, how these different algorithms work, because then you can select them according to what you see and what is working on your particular case. So far we've been using this stochastic gradient descent, this SGD. This basically tries to slide down the surface of the loss function by going on the direction of the gradient downwards, but it allows you to also include momentum. And generally you should use momentum because it speeds up training quite a lot. So when you use these objects from this class, each time you give the information on the gradients, the SGD will also store the velocity with which it is changing the parameters, and that is the part of the momentum, and it will use momentum to improve the training. From now on, we're going to use these optimizers, and also we're going to use Keras, the Keras API. So we will no longer be doing explicitly that part of using gradient tape and then calling the optimizer, but you can still choose the optimizer you're going to use. So everything is hidden inside Keras, that part, but we have the ability to choose the optimizer. Another optimizer that you can choose is AdaGrad that allows different parameters to learn at different speed. So in stochastic gradient descent, is SGD, we have one learning rate, and that one is used for all the parameters, and it's multiplied by the gradients. So parameters with smaller gradients will learn slowly, will change by a smaller amount at each mini-batch. Parameters with larger gradients will change more. AdaGrad tries to even out this by keeping a sum of the squares of the gradients in the past. So for each parameter, it keeps track of the sum of the square of the gradients for the whole training so far. And it divides the learning rate by this sum at each iteration. So one of the things this does is that parameters for which the gradients have been large will now be trained slower than parameters for which the grades have been smaller. And this compensates the difference in the magnitude of the rates. So the different parameters tend to be changing at the same velocity instead of one sum being much slower than others. Another thing is that since this divides by the sum total of the gradients so far, this means that as training progresses, the overall velocity of training starts to go down, because the sum of these squares will increase for all the parameters. So basically what this does is it evens out the velocity with which different parameters are learning, and it slows down gradually along the training, which is good for convex problems. You can imagine convex problems are those in which the loss function, the surface of the loss function, has these dips that we want to find, these holes. And so if we go slower and slower, we can find the optimum position instead of overshooting and going out the other side. So this is one option that you have. RMS prop is similar, but instead of keeping the sum of the squares of the gradients, it keeps the root of the mean of the squared gradient. So this is taking the sum of the square of the gradients, then dividing by the number of iterations, and then taking the root of that. So it's an average, not a sum. Otherwise, it works similarly to AdaGrad. So parameters with larger gradients on average will now slow down because the learning rate will be divided by that average. Parameters with lower gradients so far will tend to speed up the training because of this division, but it will not slow down training during the course of the whole training schedule, because it is dividing by a mean and not by a sum. So this mean will tend to be more or less the same over training. So this is very useful for non-convex problems, such as with recurrent neural networks. We're going to see more about this later on, but with a recurrent neural network, we are presenting sequences of data to the same part of the network, and the output of the network is also feeding into the network itself. So it's the same set of parameters that are receiving the output of previous iterations. And this is no longer this kind of problem where you're going down, we can imagine a somewhat fixed surface of the loss function to find the hole, but the whole thing keeps changing because we are using the output of the network to feed into itself and then keep changing the parameters. So RMS prop is very used for recurrent networks, and actually it's famous by being a widely used optimization algorithm that was never published. This was presented on a workshop, then everyone started to use it, and it was never officially published in a paper. A more recent optimizer, this Adam, brings together these kinds of aspects of the AdaGrad and RMS prop by looking at the past, the history of the gradients, but in this case it uses this exponentially decaying moving average. So it gives more weight to the recent gradients and then increasingly less weight to the more distant in the past. But it still will use this to scale the learning rate for different parameters. So again, parameters that have higher gradients will slow down learning, parameters with lower gradients will have a faster learning. But in addition to that, it also uses momentum, and this combination makes it very fast for training. So usually when you use Adam, you can see very fast learning on the network. But it's a bit dangerous, it's too greedy, and sometimes you have convergence problems. So Adam is a good first choice to experiment, but be careful that the results may not be as good as you can have with other optimizers if you have some bad luck and it does not converge. So unfortunately, there is no solid theoretical foundation for this. This is more or less some things work better than others. And also, as you can imagine, the actual shape of the loss function will vary a lot from different problems and different networks. So it's very hard to think of a priori which of these algorithms would be best. But one thing you can do is to experiment, so use, for example, a subset of your data and see how things work with different architectures and so on, and try different optimizers to see what works best in each particular case. Another thing that we need to do is to choose the learning rate. And basically, there's a trade-off here. If you use a small learning rate, training will take longer. It will not affect the end result using a smaller learning rate than necessary, but it will make everything slower, and so training will take longer. However, if you use a learning rate that is too high, you may have trouble finding a good spot on the landscape because the parameters keep jumping around too wildly from one point to another. And this you can notice if you see these oscillations on the training error. Having some oscillations on the validation error is not really that strange because since the validation set is a different set of data from the training set, it can happen that you make things slightly better on the training set and they get slightly worse on the validation set. But you should not have these values going up and down on the training set because you should always be decreasing the loss function on the training set. So this is an indication that you're overshooting the right spot and your training rate is too high. If you take a look at the plot of the training error and see these oscillations, you should reduce the learning rate or try a different optimizer or something like that. If the learning rate is too small, it will take too long to train. So basically, what you can do is you take a subset of your training set. Remember that if you use fewer examples, you need more efforts to train the network with the same number of examples. But if you use a smaller set, then it's easier for the network to learn the patterns in that particular set because it may be looking at a subset of the combinations that can occur in your data. So the overall training, even though you may need more efforts, may actually be faster than using your complete training set. Of course, if you use a small part of the data, you will have lots of overfitting, so that's not good for actually training the network, but it's good for experimenting and optimizing these kinds of parameters. So one approach could be use a subset of your data to make training a bit faster. Don't worry about the result because it will be overfitting, but use that to adjust the parameters like the learning rate so that you get a smoother curve here on the training error and still go as high as you can without having those large oscillations. Another thing that is important, as we saw in last week, is how we are going to initialize the weights. So remember that we need the weights to be randomly initialized because if we have neurons that have the same set of weights on the same layer, they will all have the same gradients, and so those neurons will always be copies of each other. And so they work as if they were just one neuron and not be very useful. But if we give random values to the neurons, we may easily, when we have many neurons especially, we can start to have some overflow problems because we start having numbers that are very large when we do all those sums and multiplications. So one thing that we did was to solve that problem by dividing by the number of neurons. That was just a quick and dirty method. But there are other initializers that are a bit more sophisticated. So this LeCun normal initializer chooses the weights with the normal distribution centered at 0 and the standard deviation that is the square root of 1 divided by this fan-in. The fan-in is the number of values that are coming into the neuron, so basically the number of weights in that particular neuron. The normalized initialization, or the Glorot uniform initialization in Keras, uses both the fan-in and the fan-out and uses a uniform distribution. So this is uniformly sampled between these two extremes that are the square root of 6 divided by the sum of the number of weights going into the neuron and the number of weights that are using this neuron on the next layer. This, I think, is the default initialization, but if you see here you have several initializers, and usually the default works well, but if you are seeing strange problems with not a number and so on, either standardize your data or be careful about the range of values that you are inputting into the network, or experiment a bit with different initializers to try to solve that. This normalization or standardization is important. We saw this previously, not only to avoid these kinds of numerical problems, but also because if you have different features at different scales, then it's harder to learn because different patterns there will have to be learned at different speeds, and so you make training hard. One thing that we should always do is standardize the inputs or normalize if you're dealing, for example, with images where you have some fixed range of values. For example, each color channel in a red, green, and blue image will have byte values between 0 and 255. In that case, you can just divide by 255 and everything is between 0 and 1. This would be an example of normalization. In general, if you don't have these ranges, you can use standardization, which is subtract the mean and divide by the standard deviation, as we've been doing so far, and you put everything there close to 0. Now, one thing that we always do this at the input, but if you can imagine, after passing the first layer of the network, then the output of that layer will no longer be standardized. You have the activation functions like ReLU, they can have wildly different values. So one idea here would be, just like we do for the inputs of the network, we do the same thing for different layers in the network. And this is called batch normalization, and basically for each batch it will compute the averages and the standard deviations. It's actually, even though it's called batch normalization, it's a standardization. That's an unfortunate name. But the idea is to keep running averages of the means and standard deviation of the outputs of each layer in the network, and then applying that information to standardize the output of the layer before putting it into the next layer. And what this does is not only solve that problem with scaling, but also a problem of one layer as it learns, shifting the whole set of values that it's outputting into different regions of the range. So everything can be higher or lower or something like that, which in turn forces the next layer to relearn things that it had already learned because they now no longer work. And this keeps the data, the values that are being input into each layer always centered and on the same scale, and only the shape, the patterns will change depending on what the previous layer is learned. So batch normalization reduces this need to adapt to those changes and can improve training a lot, can make training much faster. This is easy to do in Keras. We're going to see today how to use this API because you can just add batch normalization layers between the layers of neurons in your network. All these mean standard deviation and rescaling that is done is basically multiplying by constant, so it's just integrated as part of backpropagation. AutoDiff takes care of everything there, so we can just put batch normalization layers as if they were additional layers in our network. Okay, so this was, so far we've been seeing how to train the network, the optimizers and the learning rates and speeding up training with these techniques. But now we have the problem of optimizing the performance of the network. And what we want is whatever we're doing with the data, we are doing it with a sample of the possible data, with the training set, but we generally want the network to be applicable to other new data that we have. So we want to predict outside the data that we already have for training. And this leads to the problem of overfitting, which is things work very well on the training data, but then don't work so well outside because we lose generalization. We learn too much about the training data and lose the ability to predict things outside. So one way of solving this is to select the right model. If your network is overfitting too much, you can simplify it a bit, reduce the number of parameters, reduce its ability to adjust to details in the training set that do not generalize outside the training set. Or we can adjust the way the network is being trained. And this is called regularization. Basically, regularization is everything that affects the way the network is trained with the goal of reducing overfitting without changing the architecture itself, without changing the model. If you change the model, then it's model selection, you are comparing different models. So one way of checking for overfitting is to evaluate the performance of the instance we have in our model outside the training set. One method that we saw previously last semester was cross-validation. So basically, just to review this, we partition the training set into several parts. We leave one part outside for validation and the rest for training. So we obtain, for example, this discriminant with this set of points that we use for training, and now we measure the error on the large ones here, which are the validation set. And now we can switch, leaving outside another set of points, and we keep doing this through all the partition, and we average all of these errors. So this is a good way of doing, evaluating how well the model is performing if we have models that are very fast to train. If we have models that take weeks to train, then this is no longer very practical because we need to retrain the model for different sets of data. So actually, the cross-validation is very good, especially when you don't have much data. It gives you a better estimate of the true error because you're averaging over different samples of the data. But it's more computationally demanding. This is not a problem if you're doing logistic regression or something like that, but it can be a big problem if you're training deep neural networks. Generally, when you have lots of data, then having just one validation set and just doing this once, so basically you can imagine here, we leave some points for validation, we train here, and we check for overfitting there. That would be doing this just with training and validation. This is a good approach when we have lots of data, which is generally the case for deep learning, and when training our model is expensive and we don't want to repeat that several times. So cross-validation is widely used in machine learning in general, but not very used in deep learning. In deep learning, the standard approach is to have a training set and a validation set. The validation set allows us to measure the error outside the training set and then try to optimize some parameters like regularization methods that we're going to see, change the architecture of the network, things like that. Now, another thing that we generally need is an estimate of the true error. That means what would be the performance after training of that hypothesis that we obtained, the trained model, when we apply it to any future data that we can meet. So basically the true error will be the expected error over all possible data, and this is something that we cannot measure because generally we don't have all possible data labeled in order to measure the error. But we can estimate this with a set of examples outside the training set, as long as they were never used to decide and to optimize the network. And this is an important thing. We cannot generally use the validation set if we did something with that validation error, because if we use the validation error to try to improve the performance of our network, for example, changing the architecture, changing regularization parameters, something like that, then the validation error is biased because we've been fiddling with everything in order to make it as low as possible. And this will not give us an unbiased estimate of the true error. So generally, you need to set aside part of the data just to use at the end, when you did everything, to have an unbiased estimate of the true error. If you don't do that, then the validation error will generally be a biased estimate. The only exception is when you don't optimize anything. You just train the network and you have measured the error outside the training set. And if you don't do anything else, then that measure will now be the test error, because you're not using that to change anything in the procedure. But if you use that information to make changes, then you are biasing the measure by purposely trying to reduce it, and that means you need a test set in order to get an unbiased estimate of the true error. So this is the general approach. We have the training set, the validation set to improve things, and once we have everything ready, we evaluate the performance of the test set and have an estimate of how well the classifier or the network we have will be. So when you're looking at these kind of plots, training and validation, you can identify the overfitting problem or underfitting fairly easily. So if the model adapts too much to the data, the training error is low, and you can see here that it's going very close to zero. This is an example of the miles per gallon problem that we've been doing in the exercises with a very large network. This has 150, 10, 1 neurons. So you can see that the training error goes down very far, but the validation error doesn't. This means that the network is overfitting. Inside the training data it's working fine, but when you try to look outside, it doesn't work very well. So if you're doing model selection, you can try to simplify the model, reduce, for example, the number of neurons, layers, and so on, to make it simpler. Another problem that you can have is to, so this would be an example where you have a low training error, and you also have a low validation error. So this network is actually performing better than this one, even though the training error is higher, because the validation error, which is what really matters, is lower. And this is what gives us an idea of how well the network will perform outside this set. But you can have, if you go too far, for instance here, this is a 30-10-1 network, but if we have, for example, a 3-2-1 network with only these neurons, now we have training and validation error. They are nearly the same, but they are both very high, much higher than in this case. So this is an example of underfitting. In underfitting, your model is unable to learn the actual structure, the relations, or approximate the function you're trying to approximate in what you're trying to predict. So this is a problem that has no solution with this model. There is no way we can make this model perform better, because it simply is unable to find the correct parameters in the data. So if you have this kind of result, if your training error is too high, then you need a better model, you need to increase the complexity of the model. However, if you have this kind of result, one solution could be to simplify the model, but another solution could be to use regularization, to change the way the model is trained in order to prevent it from overfitting while still using the power of the model to adjust to the data. So this would be another approach. But to understand this well, I'm going to review a bit this part. We saw this last semester. We can decompose the error of any hypothesis that we have, or looking at the model, decompose the error in general of the hypothesis that we're going to obtain. into these two parts, bias and variance. The bias is a deviation between the average prediction and the actual values. So you can imagine that we are repeating the experiment, we are obtaining data and training the model. Then we obtain data, we repeat the experiment, and each time we do that, we obtain data that is distributed according to whatever the universe is making the data do, but the actual examples are different because we are randomly sampling from the universe. And so when we train the model, if we get these kinds of predictions, we notice that there is a bias here. For example, for a value here, on average, each time we train the model and we try to predict that, it gives us something that is overestimating this value. So this is the bias. It's a tendency, a deviation of the average of the predictions we get from what the actual value will be. And the high bias is an indication of underfitting. It means that the model cannot adjust properly to the data, so it's always making the same kind of error in each position. The variance is the dispersion of predictions when we repeat the training of the model with different sets, and we can see that for predicting some particular value, we are spreading out wildly here with different predictions. So this is something that increases this effect with overfitting. If our model is learning too many details that do not generalize in the training data, then it can make some wild guesses about things outside the training data, and this will make variance high. And in general, we have a trade-off between the two. If the model is too steep or underpowered, cannot adjust well to the data, we have high bias but a low variance. But as we keep increasing the power of the model, eventually we'll start having a high bias, a high variance, even if the bias is low. So this gives us this U profile on the error, because the error is a sum of these two contributions, that generally has an optimal spot here, but goes up on these two paths. But these two situations are different, and that's why it's important to understand this, because if we have a high bias, underfitting, we cannot do anything about that with that particular model. The model simply cannot bend enough to adjust to the data. But if we have high variance, we can try to mitigate that by restricting the way the model learns, and so decreasing the tendency to overshoot and to give us wildly different guesses. So with high bias, we cannot do anything about this. Variance is low, but the error ends up high because the model cannot adjust to the data. This can be solved by, for example, incorporating our model in an ensemble of models with boosting. For instance, we saw this last semester, but this is not practical to do with deep neural networks because we need families of these models. And generally, this is not a meaningful problem in deep learning, because if you are faced with this situation, all you need to do is to increase the power of your network. So that's generally a simple solution. We don't have any other good approach for this other than using a deeper network or with more neurons and things like that. What is often a problem in deep learning is high variance when we are overfitting. This happens when the model is adjusting too much. Typically, the model is too powerful for the training data that we have, and so we have more error outside the training set. This is common in deep learning because we can use very powerful models, very deep networks, and often we need to use these very powerful models because otherwise we cannot even learn correctly with the training data. So the patterns in the training data are not properly captured by the network. But it may happen that when we build a network capable of having a low training error, we always end up having a high validation error because the power we need for that particular data will be too much relative to the size of the data set that we use. But if we are in this situation, we can use regularization. So basically, regularization is any change to the way the model is trained, not the model itself, but the way the parameters are adjusted, and usually it's meant to reduce variance. And we have several different ways of doing this. One possibility is penalizing the magnitude of the parameters. So you can imagine that in overfitting, the model is adjusting too well to the data because it can freely adjust the parameters and learn things that it shouldn't. If we restrict the freedom with which it can change the parameters, we can make it a bit more stiffer, less flexible, and so reduce this problem. Basically, we can add to the loss function, in addition to whatever loss function we have to maximize the likelihood, a constant multiplied by a function of the parameters that basically will force the parameters to be small. This function can be, for example, in L2 regularization, it's the square of the vector of the parameters. In L1 regularization is the sum of the parameters, the absolute value of the parameters. But basically what we have is we have here some constant, small constant, that gives us a weight to that measure of the magnitude of the parameters, and this will tend to shrink the parameters. This is generally only on the weights of the neurons and not on the bias value, because the bias works a bit different. It just helps adjust where the neuron is firing. It's the weights that are multiplied by the inputs that will increase the ability to oscillate too much, for example, related to the Wagner-Chevanek that I mentioned as we saw before, and to these problems of overfitting. So generally, regularization is applied to the weights and not the bias itself. Now, the difference between these two is that if we are penalizing the square of the weights, this is also called weight decay, because when you have something like this, the update rule, when you do the derivatives, will subtract from the old value of each weight a fraction of what that value was. So this epsilon here is the learning rate, the alpha there is the regularization term. This will be a small fraction, but basically we are subtracting a small fraction of what the weight was every time we update the weight. One way you can imagine this is why it's called weight decay, is that if this weight is not very important to minimize the loss function, then it will tend gradually to go smaller and smaller and smaller. It will never be quite zero, but it will grow smaller at each iteration. So basically this causes weights that are not important to shrink gradually closer to zero, and it shrinks the overall magnitude of the parameters that we have in the network. L1 regularization is penalizing the absolute value of the parameters. So basically, when you compute the derivative, this is just a constant based on the sign of the parameters. It will be positive if the parameter is positive, negative if it's negative, but it will be removing always a fixed size from the parameter. So basically, this will again try to shrink those parameters that are less important, but it will actually shrink them all the way to zero. It will not be that much concerned with the overall size of the parameters, not as much as L2 regularization, but it will force parameters that are not important to go down to zero. So this basically, L1 minimizes the number of non-zero weight parameters, L2 minimizes the overall length of the vector of parameters. But in both cases, what we are doing is applying this pressure to how the network is being trained in order to reduce the flexibility of the model and prevent it from overfitting. Another approach is to use more data. So more data is better because if you have more data, then you reduce the possibility of the model being learning in a small subset of data, things that do not generalize outside that data. And in some cases, this works because we can create more data. For example, suppose that we are working on a problem of image classification and we need to identify if there are faces on the image or not. In that case, we can take one example and transform it in a way that it's still a face. For example, flip it or rotate it or change a bit the resolution, slant it, so on, apply some deformations and things like that. So all of these must still be identified as faces, but they are not exactly the same example that we are presenting. So we can augment the data by applying these transformations. Of course, this must be done in a way that is appropriate. For example, if you have faces and you use the mirror image of the face, you flip vertically, for example, or horizontally, this works, it's still a face. But if you have characters, for example, a P and a Q, you cannot just flip them because you'll turn one into the other. So depending on the problem that you're trying to solve, some of these methods may apply or not. But if you find a safe way of generating new data from the data that you have, this is another regularization method that will help you reduce overfitting. You can also do generic data augmentation by noise injection. This is basically adding a small random error or small random noise to the data as you input it into the network. You can imagine that your data is always a vector of values. Add to that with a small range, a random vector that is very close to zero but makes some small changes, so that it's still the same kind of example, so the label you're trying to learn, it's still correct, but it's not exactly the same example. And this can work as data augmentation. This can be done, applied to the inputs that you have. It can be applied to the weights on the parameters. So the network is not using exactly those weights, but with some randomness changing those values, or even to the output. There are cases where you may think that there may be errors in some labels, so we may make some small changes randomly, or we can do label smoothing. For example, when you have binary classification, you have some examples belong to class 1 and others to class 0, and you make it so that the probability of belonging to class 1 for the first examples should be 1, and for the other class should be 0. But this forces the sigmoid into extreme values, because only in plus infinity is the sigmoid exactly 1, or in minus infinity exactly 0. If we do label smoothing by reducing a bit, say for the positive class you need to have 0.95 and for the negative 0.05. In that case you do not require the network to stretch so much those values at the end. So this may prevent softmax or sigmoid, these probability estimates, from going to being pushed towards infinity, and it helps regularize the network. A very commonly used method of regularization in deep neural networks is early stopping. This example is a bit exaggerated because there is clearly a lot of overfitting here, but what I wanted to point out is that during training, the validation error is going down and then it starts going up again. So as long as we are close to the beginning of the initialization values of the network, we are improving the validation error as we improve the training error. But once we start moving too far and going into overfitting or increasing overfitting, then reducing further the training error only leads to a decrease in the performance, to an increase in the validation error. So one technique is to keep track or save the weights of these models, and then use the one that behaved better here in the validation error, or just look at how the validation error is occurring, and when you see that it's increasing, you stop training and you don't make things work. So this is early stopping, basically stop training when the validation error starts increasing. Another method that is useful for reducing variance, and one that we saw in machine learning, is to average a large number of models. We did this with bagging, for example, where we use bootstrapping to generate replicas of the training set. we train a large number of models, and then when we want to use them, we train the model a large number of times, and then when we want to use it, we use all of those different hypotheses and we average the result. Now, doing this like this would be very costly with deep neural networks, because if you need to train your network 100 times to get 100 instances, and then store everything and use everything, this will take too many resources. But there is one way of doing this implicitly, and that is dropout. During training, we randomly switch on and off different neurons. So for all the layers, we pick at random which neuron is going to be turned on or turned off. Neurons that are turned off effectively don't exist for that particular mini batch. And so for each mini batch, we are training a different network implicitly, because we are turning off some neurons, so only this part or that part of the network is being used. And this effectively is training our network as if it was a family of networks given by all the many millions of combinations of neurons that can be turned on or turned off at each mini batch. So after training like this, we rescale the weights of the neurons by the probability of the previous layer neurons being turned on. So this brings us back to more or less the same magnitude of values going through the network. This is because if we are training, if this neuron half of the time is getting inputs from these other neurons in the previous layer, but half of the times they are switched off, then actually the weights here can be much higher than what they would be if the neurons were always turned on. So we rescale this at the end, and now all the neurons are always turned on after training, but the weights are rescaled to make these things smoother and match better. Or in the case of inverted dropout, the adjustment is done during training, and then we reverse back after training to the original weights. In any case, this is the general idea. We are turning on and off neurons during training, then we rescale the weights to make this equivalent to what it should be if all the neurons were turned on. And what we have is a network that is robust to changes in where the pattern is being identified. It can be identified by these neurons or this other combination or this other combination. And so we are restricting a lot more the way the network can learn, and effectively use the network as if it was a family of networks, and we are taking the majority vote there. Another approach is adversarial training. This is something that not only can be used for training the network, but also for deceiving networks. This is an example. We have this panda image, and our classifier is telling us that this is a panda with a 57% probability. But now we take this image that is created by looking at the sign of the gradient of each pixel with respect to the loss function. So we are looking at in which direction we can change the value of the pixel that maximizes the impact on the loss function, given these particular weights that the network has. And if we add this image with a very small amount here, so this is 0.07 times this added to that one, we have something that to us looks exactly the same, because we added this with a very tiny amount. But since we are adding these values exactly in the direction that changes the loss function the most, we are now changing the classification, and the network tells us this is a given with 99% probability. So this is a problem because the network is learning on the training data to distinguish between different images, but it does not have really an understanding what the images are. It's just that it's finding frontiers there. And it may be very sensitive to very small perturbations if they are given in the right way, in this case to maximize the impact on the loss function. So adversarial training consists in adding these examples during training in order to make the network more robust and to move the discriminants away from these examples so that it does not change class simply by a small perturbation there. Usually this is a bit expensive to compute, so noise injection and things like that don't work as well as this, but it's more or less the same idea. However, this illustrates the problem with not really understanding how the network is doing classification, and it means that it can be very sensitive to this kind of deception. So this can be used in, for example, you can see things that affect facial recognition, types of makeup, or if you draw a mouse on the mask, things like that, it may deceive the network. So there are lots of these types of attacks that take advantage of the way the network is trained. But if you use that during training, you can make it more robust to these kinds of things. So basically, we saw here that we have many different possibilities. There are these meta parameters to select, not only the architecture of the network, but how to do regularization, which optimizers to use, and so on. There are several strategies. You can use all the combinations in a grid search or random search and so on, but usually there are so many combinations that basically what we end up having to do is to do manual search and try to think a bit what could be the best approach. So one generally used trick is to take a small sample of your training set. Your network will quickly overfit in that small sample, but you can use that to adjust the architecture and so on until it seems to learn where there. Then experiment with the whole training set and see if the network can learn to have a good training error on the training set. And then you check if you have overfitting and try to mitigate that problem with things like dropout, data augmentation, regularization, L1, L2, those kinds of approaches in order to minimize overfitting. So this would be the general approach to try to get the best out of your network. Okay, so to sum up, we saw the optimizers to actually determine the parameters of the network. Then we saw how to try to also optimize how the network works, selecting the best models, looking for underfitting and overfitting. Remember that underfitting is a problem that has no solution other than choosing a different model. There is no way to solve that. Overfitting can be solved by placing some pressure in the way the network is learning, or getting more data, or simulating more data, something like that. So usually we try to make our model work well on the training set, and if that leads to overfitting, we then try to solve that with these other approaches.